Right, welcome back. We're going to now talk about diazotization reactions. All right, so the nitrogen group, once installed on an aromatic ring, has some interesting attributes that can be utilized for synthetic purposes. First things first, I mentioned to you on a previous video how you can install the nitro group on benzene via a typical electrophilic aromatic substitution reaction. But I did nothing in regards to mentioning how you can install the amino group. Well, the reality is that you don't, at least not directly. But one way that you can ultimately end up with that amine group onto your benzene ring, basically form your aniline molecule, is to reduce your nitro group with elemental tin in the presence of aqueous hydrochloric acid. This reaction ultimately behaves similarly to the reduction of carbonyls, um, and it gives you an entry point into making the amine derivatives. Now, once you have the aniline derivative, you can react that further with sodium nitrite in the presence of hydrochloric acid at low temperature, pretty much ice water, if you will. Um, and what this does is it creates a very interesting group. It creates a nitronium ion that it actually serves as an excellent leaving group for the reaction. And that's such the point that I'm going to show you a variety of reactions that we can apply once we get to this diazonium salt. And just to give you another example to kind of complete the series right here, you can go from the diazonium back to the nitro group upon treating the diazonium salt with the conjugate acid of tetrafluoroborate, so tetrafluoroboric acid, and sodium nitrite at low temperature in the presence of copper. So this kind of completes the whole picture. And although at first you might be thinking, well, what's the point of doing all of this if you're just going to go back to the nitro group? Sometimes you won't have to do this, but in some instances, it might be to your benefit to change a nitro group, which is a mera directing group, an electron withdrawing group, into an amine group, which is an orthopera directing group and an activator at that. And once you do whatever electrophilic aromatic substitution you need to with this amino group, you can go back to a nitro group at the end of the picture. So synthetically speaking, that may have a case to actually be applied to, but sometimes you might not need to, but it is there in case the situation arises. All right, so first let's go through the process of forming these diazonium salts. So the first thing that happens is that in the presence of hydrochloric acid, sodium nitrite, which is a weak base, but it is basic enough to react with hydrochloric acid, it gets protonated to form nitrous acid, right? In the process, you kick out sodium chloride. Now, the nitrous acid in the presence of excess HCl can react again as a base, mind you, a weaker base, but still a base good enough to react with HCl. And in the process, you end up generating a water leaving group that once the oxygen lone pair on your nitro portion moves over to the nitrogen, it can kick out the water derivative altogether. And it is in this event that you produce what we call the nitrosonium ion, the NO plus derivative. And this molecule is very reactive, so much so that you really only produce it in situ. And you have to make sure that the temperature throughout the entirety of the reaction is kept at 0 degrees Celsius. This is not a reaction that you do within a minute, within seconds. You have to be kind of patient with it, and you have to take your time because if you don't take care of it and you don't keep tabs on the temperature, you might end up doing side reactions that will kind of bypass the whole purpose of making this nitrosonium ion salt. More about that later. But basically, when the nitrosonium ion is formed, this is done in situ, meaning that it's done in the presence of the aniline the entire way through. So as long as the temperature is cold, as long as you're doing this relatively in a slow fashion, so it's not warming up too much, what will happen is that the aniline will attack the nitrosonium ion directly to the nitrogen. That will kick away the electrons from the NO triple bond towards the oxygen, and you will form this intermediate that will still have a nitrogen positively charged, an ammonium derivative right on the nitrogen attached to the Benson ring. And what happens now is that you deprotonate that nitrogen to form the amine derivative. All right, so this molecule is still reactive. This is a molecule, technically a hydrazine derivative, but you can still undergo further protonation onto that oxygen, which is what's being shown right here, right? So you attack from the oxygen to the protons of HCl, you kick out the chloride, and the protonated derivative right here basically can undergo one little change. Specifically, when the chlorine comes by to deprotonate the molecule, it deprotonates now the nitrogen on the opposite end of the molecule, and the electrons of that NH bond relocate over to the adjacent nitrogen to form a nitrogen-nitrogen double bond. But in the process, you also kick away the electrons towards the oxygen. So now you have this nitrogen-nitrogen double bonded derivative with a hydroxyl group. And that hydroxyl group can attack another molecule of HCl, get protonated by it, and you end up ultimately generating a good Levin group, water. So it is right at this point that the lone pair of the nitrogen here on the left moves over to the nitrogen directly to its right in such a way that you kick out the water Levin group altogether, and you end up generating this diazonium salt, which is basically N2 bound directly to benzene. And to really think about this as to the implications, you have the best possible Levin group that you can hope for on your benzene ring, because this N2 is basically N2 gas, right? The moment you generate it, the moment it comes off and that no longer binds to the benzene ring, it will be a gas and it will exit the vessel completely. And not only that, even if you kept it around, N2 gas is really not a reactive molecule. It's not really a nucleophilic molecule. So the reverse reaction is really not an option. So the moment that this N2 portion of the molecule is kicked out, it's basically gone forever. And that is the big attributes, ultimately the thing that we take advantage of in this reaction. This elimination into N2 gas allows us to add any other substituent in place of the N2 derivative. So here's where the diazotization reactions kick in. So far, all I've shown you is how you make the diazonium salt, which is the middle ground, but is also the main route to generating a bunch of other substituents on the benzene ring. For instance, you could react your diazonium salt to make a nitro group substituent. We talked about this already, and this has to be done at 0 degrees Celsius. This is true for all the reactions that I'm going to list right here. So to install the nitro group from the diazonium salt, you have to introduce tetrafluoroboric acid in the presence of sodium nitrite with copper. But you could also want to introduce other things like halogens or even cyano groups on your benzene ring. So in the case of halogens, all you have to do is react your diazonium salt with copper 1 halide. The halide could be chloro, it could be bromo, it could be iodo, but it's copper 1 that you're reacting this with. Another one would be the introduction of fluorine, but unlike the reactions here with copper 1 fluoride, copper 1 fluoride doesn't actually exist, right? Copper 1 chloride, bromide, iodide do exist, but copper 1 fluoride is not really a thing. So you actually make it a different way. You react the diazonium salt with tetrafluoroboric acid, but you do this with heat. And that's to be contrasted with the first set of reactions right here, which I said, you have to do this at 0 degrees Celsius because that prevents the HBF4 from decomposing and introducing the fluoro group. If you accidentally warm up the reaction, then you will probably get a mixture of the fluoro derivative and the nitro derivative in the process. Now, the cyano group, as I was mentioning, one way to install that group, which is a good moderating electron withdrawing group, is to use copper 1 cyanide. So that works pretty well for this type of reactions. Now, another group that I mentioned not only in this set of lectures, but even in the previous class, is phenols, aromatic alcohols. This functional group is pretty important in the chemistry of alcohols. And one way to install it is to simply react your diazonium salt with water, right? Water is a better nucleophile than N2 gas, so that will be one way to do it. Although I'll let you know right here, right now, it doesn't actually work for every single aromatic molecule. If you put a bunch of substituents on the benzene ring and you try to install the phenol group, there's a chance that it might not work out, in which case you have to take other synthetic routes to get to that point. But for now, we'll leave it at this. Introduce water to your diazonium salt with a little bit of heat, and you'll get the actual alcohol derivative. And then the last one, which may seem a little bit silly, but it does have a point, synthetically speaking, is the reintroduction of the proton itself. So basically, you can change the diazonium salt for a hydrogen upon reaction of the diazonium salt with hypophosphorous acid. And the last thing I'll mention is that some of these reactions, specifically the ones that use copper as the reagent, are known as the Sandmeyer reactions. So you might hear me refer to them in such a way in the future. And then the last one that uses the tetrafluoroboric acid are called the Schiemann reactions. So, just be aware of those names in case, but generally speaking, what you'll be pretty much asked to do is to remember all these reaction conditions and the direct byproducts that you generate from using those reactants. All right, so with that, we'll stop the video right here. And in the next one, we'll start talking about synthetic examples as to how you generate certain organic molecules that have the benzene ring and substituents on it. So I'll catch you in the next video. All right.